We shall see more about congruences for a prime modulus. We have seen when is it that for a polynomial fx of degree n and monic polynomial, when is it that fx congruent to 0 mod p has exactly n solutions, and that happens if and only if n is less than or equal to p, degree of the polynomial is less than or equal to p, and fx should divide xs to p minus x modulo the prime p, that is xs to p minus x is equal to fx into gx plus p times sx. Here gx is a monic polynomial of degree p minus n and sx is a polynomial with integer coefficients. This is necessary and sufficient for fx congruent to 0 mod p to have exactly n solutions where n is the degree of the polynomial. Here polynomial fx is monic, but you can also have a polynomial whose leading coefficient is not divisible by p. Then also we can have a similar result. We take the following corollary of this. Suppose d divides p minus 1. P is a given prime and d is the divisor of p minus 1. Then the congruence x raised to d congruent to 1 mod p, that is x raised to d minus 1 congruent to 0 mod p, has exactly d solutions. In other words, see, a solution of this means a dth root of unity, x raised to d congruent to 1. Any solution of this will be a dth root of 1 mod p. So this says that if d divides p minus 1, then there are exactly dth roots of unity modulo p. In other words, if d divides p minus 1, there are exactly dth roots of unity mod p. So d divides p minus 1, that's the requirement here. Just take examples, simple examples. Suppose p is equal to 11 and try to find fourth roots of unity mod 11. So p minus 1 is 10 and 4 does not divide p minus 1. If you try to find fourth roots of unity, so take fourth powers of various elements and mod 11, what do you get? So plus minus 1 plus minus 2, plus minus 3, plus minus 4, plus minus 5 and 0. These are the elements in a complete residue system mod 11. If you take squares of these, you get 0, here you get 1, here you get 4, here you get 9, here you get 16, that is 5, and here you get 25, that is 3. So these are the squares. And if you take fourth powers, here you get 0, 1. So square of this you find out. So 16, that is 5. Then 9 square, that is 81, and that is 4. Again 5 square is 25, that is 3, and 3 square is 9. You see that the squares and fourth powers, they are the same. The set of squares equal to the set of fourth powers. How many fourth roots are there for 1? Plus and minus 1, their fourth power is 1. So 1 has only 2 fourth roots, or x raised to 4 congruent to 1 mod p has only 2 solutions here. Therefore x raised to 4 congruent to 1 mod 11 has only 2 solutions. Whereas if you take p equal to 13, how many solutions are there for x square congruent to 1 mod 13? So again you do the same thing, plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 5, plus minus 6. These are 13 elements in a complete residue system mod 13, and you take squares of these. So 0, here you get 1, then you get 4 here, then you get 9 here, then you get 16, that is 3, then 25, that is, you can say minus 1 or you can say 12, and 36, that is 10, or you can say minus 3, 10. 9 also you can say it is minus 4. Now if you take fourth powers, zero square of this 0, 1 square is 1, 4 square is 16, 16 is 3, again this is 3, then 3 square is 9, 9 is minus 4, now this is 12, minus 1 square is plus 1, then 3 square is 9, 9 is minus 4. Here you will see that the set of squares and set of fourth powers, they are not the same. Set of squares is proper subset of set of fourth powers. So 1 is a fourth power, 3 is a fourth power, minus 4 is a fourth power, modulo 13. How many fourth roots are there for 1? Plus minus 1 raised to 4 equal to 1, plus minus 5 raised to 4 equal to 1. Therefore, x raised to 4 congruent to 1 mod 13 has 4 solutions, namely plus minus 1 and plus minus 5 mod 13. These are distinct solutions mod 13. There are 4 solutions, and that is clear that there should be 4 solutions because d equal to 4, d divides p minus 1. What is p minus 1? 12. 4 divides 12. So when 4 divides 12, d divides p minus 1, there are exactly d solutions to the equation x raised to d congruent to 1 mod p. This is if and only if. So we will now prove given d divides p minus 1. So write p minus 1 equal to d into something, say e. Now consider x raised to p minus x. We want exactly d solutions for x raised to d minus 1 congruent to 0 mod p. So when does that happen? X raised to d congruent to 1, that means x raised to d minus 1 congruent to 0 mod p. That will have exactly d solutions if and only if x raised to d minus 1 divides x raised to p minus x modulo p. That was the result that we have seen. So let us see whether it divides. So write it as x raised to p minus 1 minus 1. This is x times x raised to p minus 1, you can write as x raised to d raised to e minus 1. And this is like y raised to e minus 1. That has y minus 1 as a factor. So we can write that x into x raised to d minus 1 into, now y raised to e minus 1. So y minus 1 is one factor, other factor is y raised to e minus 1 plus y raised to e minus 2, etc. plus 1. So it is x raised to d raised to e minus 1 plus x raised to d raised to e minus 2 plus and so on plus x raised to d plus 1. So this is actual algebraic factorization of x raised to p minus x, and you will see that x raised to d minus 1 actually divides, not just mod p, it actually divides, and therefore the number of solutions of this congruence, that is this congruent to 0 mod p, will be exactly equal to d. Hence, thus x raised to d minus 1 divides x raised to p minus x. So x raised to d minus 1 congruent to 0 mod p has exactly d solutions, and that is the congruence x raised to d congruent to 1 mod p has exactly d solutions, or in other words, one has exactly d roots mod p. The next thing that we shall see is Wolstenholme's congruence, which is an application of this. When is it that a polynomial has exactly degree that many solutions mod p? And we know the condition for that. So consider fx equal to x minus 1 into x minus 2 etc. x minus p minus 1. This is a monic polynomial of degree p minus 1. Now, except for 0, all other elements of the CRS 0 to p minus 1, they are solutions of this polynomial. If you take x times fx, x times fx is a monic polynomial of degree what? Degree is p, and it has exactly p solutions. Monic polynomial of degree p, and it has exactly p solutions. When does this happen? This happens provided the polynomial fx is a factor of x to p minus x modulo p. Hence, there are polynomials gx and rx, let us say sx, with gx monic of degree p minus p equal to 0 and sx belonging to zx. There are polynomials gx and sx with gx monics of degree p minus p equal to 0 and sx is in zx such that x to p minus x equal to, our polynomial is xfx. So xfx into gx plus p times sx. But gx is of degree 0. Degree 0 means constant. And if you compare the coefficients, then xfx is monic. This is a constant. And sx is of degree less than p, that is less than the degree of x times fx, or it is 0 or 0. So if you compare the coefficients of xs to p on both the sides, you will see that here coefficient of xs to p is 1, this is constant, and here the coefficient is 1. So comparing coefficients of xs to p on both sides, we see that jx equal to 1. Comparing coefficients of xs to p on both sides, gx equal to 1, and so xs to p minus x equal to x fx plus p times sx. Now this fx is x minus 1 etc. x minus of p minus 1. Now we can write these coefficients here, so roots are 1, 2 etc. up to p minus 1. So if the roots are given, you can write the polynomial in terms of the elementary symmetric polynomials coming from the roots. So we can say that this is equal to x into bracket xs to p minus 1 minus sigma 1 xs to p minus 2. Sigma 1 means sum of the roots 1, 2 etc. up to p minus 1 plus sigma 2 xs to p minus 3 minus etc. Now minus sigma p minus 2 into xs to just x, and constant term is plus p minus 1. So you can say sigma p minus 1, that is p minus 1 factorial. So 1 plus p times sx. In this calculation, I am taking p to be an odd prime, so that p minus 1 is even. So you can mention probably that let p be an odd prime. So p minus 1 is even. So here we have some convenience. Only p equal to 2 we are avoiding. So what are sigma I? Where sigma 1 etc. sigma p minus 1 are elementary symmetric polynomials. In 1, 2 etc. p minus 1, the roots of fx. Thus sigma 1 equal to 1 plus 2 plus etc. plus p minus 1. Now what is sigma 2? So it is sum of the products of the roots taken two at a time. So it is product I into j, 1 less than equal to I less than j less than equal to p minus 1. And so on. What is sigma p minus 1? It is the product of all the roots. So 1 into 2 etc. up to p minus 1, that is p minus 1 factorial. Now if you compare coefficients for x raised to b minus x equal to this polynomial and compare the coefficients mod p, what do you get? So x raised to p and here also x raised to p, so you don't get anything new. Minus 1, that is coefficient of x here, and here the coefficient is, so x times sigma p minus 1, so coefficient of x is sigma p minus 1, that is p minus 1 factorial. And so it means that sigma p minus 1 is congruent to minus 1 mod p, because here we have p times sx. So all coefficients are divisible by p there for that part. This is a polynomial where all coefficients are divisible by p. What about sigma 1? Sigma 1 is the coefficient of x raised to p minus 1. Here coefficient of x raised to p minus 1 is 0. That means sigma 1 is congruent to 0 mod p. So sigma 1 is 0 mod p, sigma 2 is 0 mod p, sigma 3 is 0 mod p, up to sigma p minus 2. All of them are 0 mod p, divisible by p. And that's what you will see here, that 1 plus 2 plus etc. up to p minus 1, what is that? This is actually equal to p into p minus 1 by 2. And this is something which is divisible by p. Okay, because p is an odd prime and 2 doesn't divide p. 2 divides p minus 1. So it is something into p. So not only sigma 1 is divisible by p, we get all these elementary symmetric polynomials in 1, 2 etc. up to p minus 1 as divisible by p, except this last one, that is sigma p minus 1, and sigma p minus 1 is congruent to my p minus 1 factorial. So let us call this as star. This x raised to p minus 1 is equal to this. Let us call that as star. What do you get from star? Hence, from star, sigma 1 or sigma I in general is congruent to 0 mod p for 1 less than equal to I less than equal to p minus 2. Okay, sigma 1 etc. up to sigma p minus 2, all of them are divisible by p. And what is sigma p minus 1 is congruent to minus 1 mod p. That is the coefficient of minus x. So this minus x coefficient is minus 1. That is congruent to sigma p minus, that is congruent to sigma p minus 1 mod p. And this is your Wilson's theorem. Because sigma p minus 1 is nothing but p minus 1 factorial. So p minus 1 factorial congruent to minus 1 mod p is Wilson's theorem. But here, by the whole procedure, we are getting more information that all the other elementary symmetric polynomials, sigma 1, sigma 2, etc. up to sigma p minus 2, they are divisible by p. That is additional information that you get here. Okay. Now, x minus 1 into x minus 2, etc. x minus of p minus 1, this is x raised to p minus 1 minus sigma 1 x raised to p minus 2 plus etc. plus sigma p minus 2 x plus sigma p minus 1. Okay. Now in this you put x equal to p. There is a sign here, I should have minus sign, and here is plus sign, that's right. If you put x equal to p here, this is p minus 1, p minus 2, etc. p minus of p minus 1, that is 1. So this becomes p minus 1 factorial equal to p raised to p minus 1 minus sigma 1 p raised to p minus 2 plus etc. minus sigma p minus 2 into p plus sigma p minus 1. But sigma p minus 1 is p minus 1 factorial, that we have already seen. So you can cancel this p minus 1 factorial and this p minus 1 factorial. So cancelling, p minus 1 factorial and then dividing by p. So here we further assume that p is bigger equal 5. See what you get. So p raised to p minus 2 minus sigma 1 p raised to p minus 3 plus etc. minus sigma p minus 2, that is equal to 0. Now observe that sigma 1, sigma 2, etc., sigma p minus 3 are all divisible by p. So here sigma p minus 3 has coefficient as p. So sigma p minus 3 multiplied by p, previous term to this, that is divisible by p square. And all these terms are divisible by p square. So if I call this as double star, hence all terms in double star before sigma p minus 2 are divisible by p square, not just p but by p square. And so what can you say about sigma p minus 2? Hence sigma p minus 2 is divisible by p square. So we can say sigma p minus 2 congruent to 0 mod p square This congruence is called Wolstenholme's congruence. So by this whole study, we are getting that sigma I are congruent to 0 mod p and sigma p minus 2 is divisible by p square. Let us do this problem that let P be a prime bigger than or equal to 5. Show that if we write 1 upon 1 plus 1 upon 2 plus etc. plus 1 upon p minus 1 as a upon b with GCD of a and b equal to 1, then p square divides a. P square divides the numerator of this rational number. See, it is somewhat easy to see that the numerator of this is divisible by p. That is somewhat easy. 1 upon 1 plus 1 upon I and 1 upon p minus I. What can you say about this? This is, if you take this together, p minus I plus I divided by I into p minus I, and this is p upon I into p minus I. So doing like this, you will see that if you call that sum as S, so what is 2 times S? 2 times S equal to this p upon I into p minus I, p upon I into p minus I. Such a thing you can do for every I. So it is summation I equal to 1 to p minus 1. Okay. This I 2 times S means S and S together, you write it in the increasing order of I and then write in the decreasing order. So I and p minus I, 1 and p minus 1, 2 and p minus 2, etc. When you combine these, you get p upon this, which you can write as p into summation I equal to 1 to p minus 1, 1 upon I into p minus I. If you simplify this is some rational number. This is p into, let us say, a dash upon b dash, where b dash is the LCM of all denominators. B dash equal to LCM of denominators but what are the denominators available? 1, 2, etc., p minus 1. These are the numbers which will come in the denominator and they are coprime to p. Therefore, the LCM of denominators is also coprime to p. So b dash is coprime to p and therefore this p into a dash, that is divisible by p. So numerator of this 2 times s is divisible by p. So numerator of 2 times s is divisible by p. There is no possibility of cancelling p from the denominator because denominator is coprime to p. And what does that mean? You can say that s also has the same property. So numerator of s in the list form is divisible by p. This is a simple fact. Just take together 1 upon I and 1 upon p minus I. That gives us divisibility of this sum s by p. That is, its numerator is divisible by p. But in this problem, what we want is numerator is divisible by p square, more than what we have done here. This just can be done by adjusting terms, taking terms together. If you want to get divisibility by p square, we shall use the Weierstrass congruence. So p square, consider what is s? 1 upon 1 plus 1 upon 2 plus etc. plus 1 upon p minus 1. So suppose you take common denominator as p minus 1 factorial. What do you get here? Numerator will be all terms from 1 to etc. up to p minus 1 except the number 1. Here numerator will be 1, 3, 4 etc. up to p minus 1. That is 1 to p minus 1 except 2 etc. So the numerator of I, when you do this adjustment, it will become, so let me write this as 1 star plus 2 star plus etc. plus p minus 1 star divided by p minus 1 factorial, where what is I star? Means the product of the numbers from 1, 2 etc. up to p minus 1 except the number I. That is I star. So 1 star means product of all other numbers, 2 star means product of all numbers other than 2 from the set 1 to p minus 1. And the common denominator is p minus 1 factorial. What is this? Therefore S equal to, the numerator is now sigma p minus 2. Numbers p minus 2 numbers taken at a time and sum divided by p minus 1 factorial. And in this note that this denominator is not divisible by p, whereas the numerator is divisible by p square because of the Wolstenholmes congruence. Now, p minus 1 factorial is coprime to p, and sigma p minus 2 is congruent to 0 mod p square by Wolstenholmes congruence. Hence, writing S equal to A upon B with AB equal to 1, we see that P square divides A. In other words, P square divides the numerator of the sum 1 upon 1 plus 1 upon 2 plus etc. plus 1 upon P minus 1. So next time we shall see how we apply these to primitive roots, the concept of primitive roots mod P. Okay.